which will be given by Armen Sergeev. Professor Armen Sergeev is the Vice Director of Steklov Institute in Moscow. He is the Vice Chairman of the European Mathematical Society and a great friend of Georgian mathematicians. He is a famous mathematician in his field, in mathematical physics, and he will speak about Sobolev spaces, space of half-differentiable functions and quasi-symmetric homeomorphisms. Ძირფასო მეგობრებო, ახლა ჩვენ მივიწყებთ პირველი მოხსენებით, რომელიც უნდა გააკეთოს პროფესორმა Armen Sergeevმა. Armen Sergeevi არის სტეკლოვის ინსტიტუტის დირექტორის მოადგილე პროფესორი და ევროპის მათემატიკოსთა კავშირის ვიცე-პრეზიდენტი, ცნობილი მათემატიკოსი მათემატიკური ფიზიკის დარგში. მისი მოხსენების სათაური არის ნახევარწარმოებადი ფუნქციების Sobolev's სივრცეები და კვაზისიმეტრიული ჰომეომორფიზმები. Please.
Thank you very much. Marjova, I am very grateful, first of all, to Professor Roland Sergeev and the organizing committee for the invitation and giving me a possibility to speak here on this very important occasion, 125th anniversary of academician Moskilishvili. Here is my talk. First of all, I start with introduction. My talk is motivated by interaction between the theory of quasi-conformal maps and string theory. Unfortunately, I will have no time to explain what is the string theory, but it is in fact my main motivation for this talk. The methods we are using arise from the non-commutative geometry, and I will start with recalling some basic ideas of this geometry. The origin of non-commutative geometry lies in the theory of commutative Banach algebras, as was initiated by Gelfand, Naimark, Mazur, and other mathematicians in the middle of the 20th century. The main idea of their approach was the reformulation of topological properties of compact spaces in terms of the algebras of continuous functions on such spaces. That was a revolutionary idea at this moment. In more detail, suppose that X is a compact Hausdorff topological space, and A, C of X, the notation, is the algebra of all continuous functions on X. As we all know, this is a commutative Banach algebra with unit, which is naturally associated with X. So we can associate with topological space X some commutative Banach algebra of continuous functions. Conversely, if A is an arbitrary commutative Banach algebra with unit, we can consider the space M of A of its maximal ideals, or, which is the same, of its multiplicative functionals, so multiplicative and linear mappings. This space, according to a famous theorem of Banach-Alaoglu, this space is compact in the weak star topology. So we can associate with the Banach algebra A with unit the compact topological space X, the space of maximal ideals of this algebra. It means, in other words, that constructed mappings define an equivalence of the following categories. One category is a category of compact topological spaces with continuous maps as of morphisms, and the other category is commutative Banach algebras with unit, with morphisms given by continuous homomorphisms. In fact, the compactness condition which we have imposed on the considered topological space is not essential. Indeed, if X is an arbitrary Hausdorff topological space, we can consider its one-point compactification, X hat. This compactification operation on topological spaces corresponds in terms of the commutative Banach algebras to adding of unit to the original algebra. And the main achievement of this theory was reformulation of spaces of topological spaces topology in terms of commutative Banach algebras. Let me give you one more example of such interpretation of topological objects in terms of commutative Banach algebras. Let E over X be a vector bundle over a compact topological space X. We denote by gamma XE the space of continuous sections of this bundle, the sections of this bundle. It is a left module over the algebra C of X because we know that we can multiply sections with continuous functions. But this is not just a arbitrary module of this kind. This module has the following characteristic property. It is projective. What does it mean? It means that this module can be realized as a direct sum in a free module over C of X. What does it mean? In more detail. If we take our bundle E over X, we may complement it to a trivial bundle by adding an appropriate bundle E prime over X, so that the direct sum of E and E prime is the trivial bundle over X. For example, if E is a tangent bundle of some submanifold in Cn, we can take for this additional complementary bundle the normal bundle. Then the direct sum will be the trivial bundle. Since E plus E prime equals this trivial bundle, that means that the space of sections of E and the space of sections of E prime, if we add them, sum them together, they will give sections of this trivial bundle. So this is just vector functions on X. So this is just direct sum of C of X. So we have constructed, for a given vector bundle, we have constructed a supplementary bundle E prime so that gamma of E is direct summed here. So we have shown that any projective, any vector bundle is in fact projective in this sense. What is more surprising is the converse assertion, which was proved long ago by Swan and Sergeev. This theorem asserts that this functor gamma, the functor which associates the space of sections with a given vector bundle, establishes the equivalence of the following categories. One category is purely topological, this vector bundles over X, and the other is finitely generated projective models over C of X. Again, we have translated topological properties of vector bundles in terms of purely algebraic. Now we can formulate the one of the main goals of the non-commutative geometry. It is the following. Extend the described interpretation of topological objects in terms of commutative Banach algebras to basic objects of analysis and differential geometry. So we want to formulate the properties of function theory and differential geometry in purely algebraic terms. Why it is interesting and why it is important, maybe I will say at the end of my talk. However, to achieve this goal, we cannot restrict anymore to the class of commutative Banach algebras and have to employ the non-commutative C-star algebras of linear operators in Hilbert spaces. So we cannot restrict only to commutative Banach algebras, but should use also operator algebras. In my talk, I shall give several examples of interpretation of various classical objects in terms of Banach algebras of bounded operators in Hilbert spaces. The arising calculus is called following Alain Kohn, who is the main person behind this non-commutative geometry. It is called the quantum calculus. So I will speak about quantum calculus. What does it mean? First of all, since it's quantum calculus, I should recall you a little bit about what is quantization, because it will be necessary for the sequel. Let us recall first the classical Dirac definition of quantization. First of all, what we are quantizing? We are quantizing classical systems. What is classical system? The classical system is represented by a pair, MA, where M is the phase space of the system, and A is the algebra of observables. The phase space M, what does it mean, the phase space M? In mathematical terms, this is a familiar object. This is a smooth symplectic manifold with symplectic form omega. So quite familiar object to mathematicians. The algebra of observables maybe is not so familiar, but this is also simple. This is just an arbitrary Lie subalgebra of the Lie algebra of all real valued smooth functions on our manifold M. This is a Lie algebra because we can introduce Poisson bracket, which is determined by this inflective form omega. So any subalgebra of this C infinity, in particular we can take the whole C infinity, is called the algebra of observables. So we have a pair, phase space and the algebra of observables on this space. What does it mean, the quantization of this classical system represented by such pair? The quantization means an irreducible linear representation of observables from this algebra A by self-adjoint linear operators. This is notation for self-adjoint linear operators, acting in some complex Hilbert space H, which is called the quantization space. This is definition. Of course, to construct concrete modules, we should consider concrete realizations of this H and concrete representations in this space. And that's what I will do later. It is required it is required also that this representation R should transform the Poisson bracket, which I denote by the curly brackets, into a commutator of these operators. So the commutator in the usual sense of operator theory. Here should stand also Planck constants here, but I set Planck constant equal to 1 because I will not deform this Planck constant. We also require the normalization condition that the function equal to 1 goes to identity operator. So this is the definition, classical Dirac definition of that quantization. These quantization operators, R of F, which arise in concrete examples, are usually unbounded. So we always assume that all of them have a common definition domain, which is dense in this Hilbert space H. Also, it is easier sometimes to deal with complex algebras of observables, which I denote A sub C, which are provided with involution. So this star operation. In this case, the observables from AC under quantization will be represented by, not by self-adjoint, of course, operators, but by some closed linear operators in H. Involution in AC should correspond to Hermitian conjugation in this space of operators. So this is the definition of Dirac. Alekhon proposed another definition of quantization, which turned out to be better suited for our goals. And let me give you another definition, which I will use this another definition, which is proposed in non-commutative geometry. In Cohn's approach, a classical system is again represented by the pair M and Gothic A, where M is again the phase space as before, while the algebra of observables A is a complex associative involutive algebra, which is provided with exterior derivative D. This is a new object, exterior derivative. The quantization of this system is given by the reducible linear representation pi of observables from A Gothic by closed linear operators acting in H. The exterior derivative operator should descend under this representation, should go under this representation to the commutator with some symmetry operator S, which is a self-adjoint operator in H with square equal to identity. So this is a definition of Kohn, and shortly we can say that the differential of F, the usual differential of F, should go to what we shall call quantum differential. Quantum differential is the commutator of S with the image of F, with this operator pi of F. This will be quantum differential. So this is the first step in quantum calculus. This definition of quantization may be also reformulated in the language of Lie algebras. For that, we should consider the algebra, which I denote der A, of derivation of this algebra A. That is linear mapping satisfying the Leibniz rule. Then, as it is well known, this der A is a Lie algebra, since the commutator of two derivations is again a derivation. And in terms of this algebra of derivation, the quantization means simply an irreducible representation of this Lie algebra der A in the Lie algebra of linear operators in H, provided with commutator as a Lie bracket. So this is another definition if you prefer to use Lie algebra language and not associative algebra language. So we have given two different definitions of quantization, well adapted to the case when the algebra of observables consists only of smooth functions on M, as we have assumed up to this moment. In fact, in the smooth case, there is not much difference between these two approaches. Why? Because the differential d of f of observable from this associative algebra is symplectically dual to Hamiltonian vector field xf, which establishes a relation between associative algebras agotic and the real algebras Hamiltonian vector fields, or is the same of Hamiltonians f generating this vector field. So while we are speaking about a smooth object, that's not much difference. So no need to introduce another definition. Why we have introduced it, or why Alain Kohn introduced it? Before I say this, let me say that the symmetry operator, which I also was an ingredient in quantization, is determined by polarization of the quantization space. So we should have a decomposition of quantization space in this two sum of infinite dimensional closed subspaces, H plus and H minus. If we have this decomposition, then S is simply equal to identity here and minus identity here. So this is the correspondence between these two definitions of quantization. But for applications in quantum physics, and I would say in function theory, we have to consider also the algebras containing non-smooth functions. In this case, the Dirac definition loses its sense, because what is the Poisson bracket of non-smooth functions? We don't know what is this. In Kohn's approach, the differential of a non-smooth observable f is also not defined in the classical sense by evident reasons. But it may happen that its quantum counterpart, this quantum differential, is correctly defined. Surprising. But I shall explain this in an example. Consider, for example, the most simplest algebra which we can imagine. This is the algebra of bounded complex valued functions on the circle, S1. Then any function from this algebra, which is bounded function, of course determines a bounded multiplication operator, MF, in the Hilbert space L2 of S1, which acts by this form just by multiplication. Since F is bounded, then it's clear that this is correctly defined operator. So we have a representation. Now we should introduce, according to Kohn definition, we should introduce the symmetry operator. The symmetry operator S on this A2 of S1 is given by the Hilbert transform. The Hilbert transform is given by this formula, where PV means principal value sense. This is a definition of principal value sense of this integral. So we just cut out a symmetric segment, then integrate, and then go to the limit. Of course, I will identify functions on S1, functions of Z, with functions of phi, which are given on the interval. The Hilbert kernel in this formula, I recall that this is a Hilbert kernel. In this formula is given by this maybe not very pleasant formula, but if we take phi going to psi, then this kernel behaves like Cauchy kernel. And if we would stay not on S1 but on the real line, this will be precisely Cauchy kernel. But we are on. It's more convenient for us to stay on the unit circle. Then this operator, which I have introduced, S, has precisely the properties which I have quoted before. It means that this is self-adjoint operator, which with square equals to 1. And this is the fact which was, I think, first proven by academician Moskilishvili. At least I learned about this fact from his book on singular integral operators. Probably this is the only place where I communicate with academician Moskilishvili. Okay, that's why I have chosen this topic to speak about. Okay, the differential of a general observable f, I recall that this is just bounded function, is not defined in classical sense, of course. But this quantum analog is correctly defined as a bounded operator in H. This operator, I recall, this is commutator with an operator of multiplication by f with Hilbert transform. It is bounded. Moreover, we shall see that it is bounded in a broader space. I shall say about this later. Namely, it's easy to compute it directly. dq of f is an integral operator with the integral on N2, with the integral kernel, which I denote by kf, and which is just this Hilbert kernel k phi psi, multiplied by the difference between f of phi and minus f of psi. So if we consider the limit phi close to psi, then this kernel behaves like, up to some constant, like this finite difference derivative. Moreover, if we consider the classical limit of this operator dqf, what does it mean? We restrict this operator to smooth functions and then take the trace on the diagonal of this integral operator. Then, of course, we shall get just multiplication operator by f prime. So the quantization procedure in this case essentially reduces to the replacement of the usual derivative by its finite difference analog. So to quantize in this simple case, we just replace operator multiplication by f prime by the integral operator with the kernel given by finite difference of phi. The quantization determined by this correspondence f associated with dq of f, which is integral operator in L2, is called the quantum calculus by analogy with finite difference calculus. That's why called it quantum calculus. So I have explained what is quantum calculus. Now, why it is interesting to consider this quantum calculus? The idea is that we can give an interpretation of function theoretic properties of bounded functions in terms of operator theoretic properties of the corresponding operators, quantum differentials dq of f in H. And I want to demonstrate you that it simplifies greatly some assertions from function theory. For example, here, let's consider some simple classes of operators, and let's try to understand what corresponds to these operators in terms of functions spaces. For example, let us ask when dq of f is an operator of finite rank, the most simple operator in Hilbert space. It turns out that dq of f is an operator of finite rank if and only if f is rational. This is Kronecker theorem. Probably some of you know it, but it's just reformulated in new terms. But this is Kronecker theorem. The second assertion, when duq of f is compact operator. It turns out that it is a compact operator only and only if f belongs to the class of vanishing mean oscillation functions. I will introduce it a little bit later. But it's quite exotic space outside function theory, quite exotic space. And dq of f is a bounded operator if and only if f belongs to the class BMO, which I just talked about this. So this dq of f is bounded operator not only for bounded functions, but also in this class BMO, bounded mean oscillation. Before I give the definition of these spaces, VMO and BMO, which probably you don't know, I should say that you see that in terms of operators, they are very simple properties. Finite rank, compact, bounded, but in terms of function theory, this VMO and BMO are not so trivial spaces. So in some cases, it really simplifies the understanding what is going on in function theory. Let me recall the definition of this class BMO and BMO. It's more convenient to do it for functions defined on the real line. If we have such a function, which is locally integrable, we can consider the average of this function along some interval of length modulus I. This is a usual notion. If this supremum of these integrals, where we subtract from f this mean value, this average, so if all this supremum over or I are finite, then we say that f belongs to BMO. To say it more simply, you can say that apart from bounded function, it also contains some logarithmic functions, logarithmically growing functions. To introduce VMO, we should use the maximum function and delta of f. The definition is just before. Is just like here, but only we take the supremum over all intervals of length less than delta. If all this and delta, for all delta, are bounded, then function, as I said, it belongs to BMO. And we say that this function belongs to VMO if this function tends to 0 for delta going to 0. So you may forget about these definitions, but I could not, of course. You just, I say once again that these are quite exotic spaces maybe for people outside function theory. But in terms of operators, they have very simple interpretation. And I will give one more interpretation of the Sobolev space of half-differential functions in terms of this quantum calculus later. Note that in the considered example, we were not able to construct the classical algebra of observables which are associated with this algebra A, since the classical differential d of f of a general observable or general bounded function was not defined. So in fact, we had no classical algebra as I defined it before, in the sense of Dirac. Instead, we have constructed directly the quantum algebra of observables generated by operators by these quantum differentials with f of bounded functions. So in order to deal with observables arising in physical applications and in function theory, I should add, we have to change our original point of view to the opposite one, trying to construct first the quantum algebras of observables, and only after that their classical counterparts. So that's the main idea behind what I will say later. And now I come to the notion which was pointed out in the title, quasi-symmetric homeomorphism, to theory of quasi-conformal maps. Let me first recall you quite shortly what are quasi-conformal maps. Сколько времени? Да. Еще 15 минут. Еще 15 минут. Спасибо большое. Хорошо. So first of all, let me recall what is quasi-conformal map. Suppose we have an irritation preserving homeomorphism of the unit disk, which I will denote by D, and the homeomorphism I denote by W, which has locally integrable derivatives. Then it is called quasi-conformal if there exists a bounded function mu in this unit disk with the L infinity norm strictly less than 1, such that the following Beltrami equation holds almost everywhere in D, in the unit disk. The equation is like that. D bar derivative of W equal mu times D derivative of W. So for example, if mu is identically 0, we get here a Cauchy-Riemann equation, and it means that in this case, our definition reduces to the definition of conformal maps. I recall that a conformal homeomorphism may be characterized geometrically as follows. If we consider the tangent map at an arbitrary point of Z, and consider the tangent map at this point, which is associated with W, then it sends the circle centered at the origin of this tangent space again to the circles centered at the image. So if we consider map, so this is the unit disk, this is the unit disk, and here is a point Z, then we have the map W sending this to the point W of Z, and we consider the tangent space here. Maybe I should point like that. And the tangent space here. Then the unit circles here goes to the unit circles here. This is one of the definitions of the conformal map. You can define the quasi-conformal maps in the similar way. Namely, the map is quasi-conformal if for every Z and every its image W of Z, it sends the circle centered here to the ellipses here, centered again at the origin, with eccentricities of this circle are all bounded by the function k, which doesn't depend on z. So this is the definition of smooth quasi-conformal maps. And in non-smooth case, I gave you the definition before. Here are some basic properties of this quasi-conformal maps. Quasi-conformal homeomorphism of the unit disk can be continuously, in fact, held up continuously, extended to the boundary to homomorphism over S1. So they are a little bit smooth. They are not completely smooth, but smooth in this Hölder sense. The composition of quasi-conformal maps is again a quasi-conformal map. The same is true for the inverse of quasi-conformal map. It means that quasi-conformal automorphisms of the unit disk, they form a group with respect to composition. And the last property is that the uniqueness property. The solution of the time equations are uniquely determined up to conformal maps. So conformal maps are considered as negligible in this case. Namely, if we have two solutions of the Beltrami equation with the same Beltrami differential mu, their decompositions are all both conformal. So up to conformal maps, the solution is unique. Now the main definition, which was in the title of this chapter. An irritation preserving homomorphism F of unit circles called quasisymmetric if it extends to a quasi-conformal homomorphism of the unit disk. So this is the definition. We know that if we have quasi-conformal homomorphism, it extends to the boundary. And now we are interested in the question when a given homomorphism of the unit disk can be really extended to the unit disk. I'll give the answer to this question a little bit later. And now I just say that since the quasi-conformal automorphism of the unit disk form a group, the same is true for quasi-symmetric homomorphism of S1. So they form a group which is denoted by QS of S1 and will play an important role in the sequence. As I said already, the question is when a given homomorphism of S1 can be extended to a quasi-conformal homomorphism of the unit disk. The answer is given by the famous theorem, which is called Berling-Alfors theorem, which is easier to formulate in the case of the upper half plane. Before I formulate it, let me say a few words about it, because the story of this theorem was quite interesting. You see that it is written, Berling is written first. And that was Alfors always insisted that Berling was made a main contribution to this theorem. And he insisted that it should be written first here. In fact, Berling, who was, Alfors was a from Swedish minority in Finland. And during the war, when Finland joined the Nazi bloc, he immigrated to Sweden, where he was invited by Berling, a famous mathematician, famous Swedish mathematician. And Alfors was so excited about this theorem that he, in one of the conferences, he explained what is this theorem and what is the main idea which was due to Berling. After the talk, Berling came to Alfors and said, "How could you speak about unpublished result?" Of course, Alfors was shocked by this. After that, they start to speak together. They didn't talk to each other until a few years before Berling died. So that probably explains what kind of person was Berling. Now, I introduce, before I formulate the Berling-Alfors theorem, I formulate the condition which guarantees that this given homomorphism can be extended quasi-conformally to the unit, not to the unit disk. I consider the case of the upper half plane H. Let us call, if we have a quasi-conformal homomorphism of the upper half plane, the boundary value is orientation preserving homomorphism of R, of the real line, which is given by monotonely increasing function f. We call such function f quasi-symmetric. This is a new definition of quasi-symmetricity. If there exists a function c greater than 1, which satisfies to this very strange condition. As you see, if this is, in fact, if you divide here by t and multiply by t, this is the product of two finite difference derivatives. Very strange condition, but it turned out that this condition is precisely what is needed to extend the homomorphism of the real line to the upper half plane. So here is the formulation. Let f satisfy to this condition, which I just pointed out to you. And then, this is the theorem of Berling-Alfors, then it can be extended to a quasi-conformal homomorphism of an upper half plane with boundary value equal to h. So this is what I wanted to say to you about quasi-conformal maps. And now you can ask what is the relation of these quasi-conformal maps to what I was talking about before. The relation is via this Sobolev space of half-differential functions, which I introduce now. So here is the definition of the Sobolev space. Probably many of you know what is this. This is the Hilbert space, which I denote by V, and the standard notation H sub 0, 1 over half S1 to R. It consists of functions from L2, which have Fourier series of this form. So you see here, there is no initial term, because this corresponds to 0 here. So the average over the circle is 0. This condition is condition of reality in order the function will be real valued. But the main condition is the finiteness of the Sobolev form of order 1/2. So this is a condition of Sobolev norm of order 1/2. So you see here is n to the power 1 and fn to the power 2. So it's 1 over 2 is here, it's 1 over 2. So this is the definition of Sobolev space of half-differentiable functions. This is very interesting space and very important and raising many different problems. For example, we can introduce the inner product. Inner product is given by this formula. And according to Cauchy inequality, it's correctly defined on H. And this is the biggest from Sobolev spaces on which this inner product is defined, well defined. This space can be also provided with symplectic form, which is given almost by the same formula, but here instead of real part, we take imaginary part. So this space has both this inner product and this symplectic form, which are well defined, and in fact they are compatible with each other in the sense which I will speak about. We can also consider complexification, which I denote by V super C of V. There's a complex Hilbert function, which is given by the same definition, the same definition as before, as in the real case. We only drop out this reality condition, otherwise the definition is the same. Now, what is the relation with quasi-conformal maps? We recall that, we know that the group of quasi-symmetric homeomorphisms, you remember this homeomorphism of S1, which is then quasi-conformally to the unit disk, it acts on the Sobolev space V, just by reparametrization. Indeed, if F is such a homomorphism of S1, then we can define change of variable operator TF, which is just simple change of variables, and we subtract the average to have the average 0. And this is the famous theorem. This is the most important theorem for me for applying non-commutative geometry to this case. Namely, this is Nack-Sullivan theorem. Probably you know Dennis Sullivan, but Subhashis Nack was a very talented Indian mathematician who unfortunately died very early. I think he was under 50. Maybe he was the main person in the theorem. He was maybe the main person under the theorem. So the theorem asserts the following, that this operator TF maps the space, the Sobolev space of half-differential functions into itself, if and only if F is quasi-symmetric. That means that quasi-symmetric group of quasi-symmetric transformations is directly connected to this Sobolev space and vice versa. So they are closely related, like twins. The action of the operator TF, if F is quasi-symmetric on the space F, preserves the symplectic structure. That means that this action is very natural from the point of view of physics, but because for physicists the most important, as we saw, this is symplectic form, because it defines the phase space. So we have defined the action of the group of quasi-symmetric homeomorphisms on the circle, on the Sobolev space of half-differential by parametrization. If this action would be smooth, then we could define the classical algebra of observables associated with this group. We need this to define classical system. Yes, it's Lie algebra and then quantize it. So if the action would be smooth, we just consider the Lie algebra and then quantize, and everything goes like Dirac has pointed to us. However, this group, of course, acts non-smoothly on V because it consists of non-smooth homeomorphisms. So it is impossible to construct its Lie algebra on the classical level. Nevertheless, we can construct a quantum Lie algebra associated with this group. And this, again, this idea, first construct the quantum system, and then from this quantum system, try to understand what the classical system. For that, we introduce the quantum differential dqf associated with the function, quasi-symmetric function. In fact, the definition is almost the same as I given to you before. Only this is again an integral operator of this form, where the kernel is this Hilbert kernel multiplied by the difference. But now I consider it not in M2, but in the space of in the Sobolev space. In terms of the quantum differential, we can give the following categorization of the Sobolev space of half-differentiable functions, as I promised to you. A function f belongs to the Sobolev space EC if and only if its quantum differential is a Hilbert-Schmidt operator. Moreover, the Hilbert-Schmidt norm of this operator dqf coincides with the Sobolev norm of the function f. So this is one more in the list of these interpretations, correspondences between function theory and operator theory. This is one more assertion. Maybe I should recall what is Hilbert-Schmidt operator. I'm not sure that everybody knows his. This is in fact L2 operator, L2 space, so to say. Formally, the definition is the following: the linear operator between two different Hilbert spaces is called Hilbert-Schmidt. If for some orthonormal basis in the first of this space, this series of this norm of actions of T on this base is finite. Square norm is finite. Of course, if it is true for some orthonormal base, this is true for any other. And moreover, this expression doesn't depend on the choice of orthonormal bases. Now we define the Hilbert-Schmidt norm of this operator precisely as this square root of this quantity. Then the Hilbert-Schmidt operators form a certain complex Hilbert space with respect to this Hilbert-Schmidt norm. That's why they are so important, because usually we know that operators on Hilbert space form a Banach space. Now I'm almost finished. I'm finished. Now we can define the quantum algebra of observables associated with the group QS of a quasi-symmetric homeomorphism of S1. Namely, we denote by A cube, cube means quantum, the algebra generated by quantum differentials F of F, with F quasi-symmetric, which acts in the Sobolev space of half-differentiable functions, EC. This is precisely the desired quantum Lie algebra of observables associated with QS of S1. So the quantum Lie algebra of observables is formed by these quantum differentials of quasi-symmetric homeomorphism of S1. This is the definition. In particular, it can also serve as a replacement of the non-existing classical Lie algebra of the group QSS1. So as we know, there is no Lie algebra associated with this action of quasi-symmetric homeomorphism. So what to do? We know that Lie algebra theory or Lie group theory acts only in the case when we have smooth actions. But here is what you can do. If you have non-smooth actions, then you should consider not Lie algebras, but quantum Lie algebras associated with this space. And I have explained how to do this. Do I still have some time?
5 minutes.
Won't you? 5 minutes, okay. Who is the different opinions?
I am chairman.
You are the chairman, so I follow you. So I have a small time.
He's sitting on the place of chairman, that's why you're mistaken.
That's why it was misleading for me. That's why I couldn't. Yeah. So maybe I just say a few words at the end, just philosophical. That's not mathematics, but philosophy. Why should we need this translation? I have to explain to you how to translate some objects of function theory, topology. In fact, the same can be done for differential geometry in terms of algebra. Why do we need to do this? Why it is interesting? The reason, at least as I explained to myself, is the following. You know that in physics, quantum mechanics is well-established mathematical theory. It's more or less rigorous. But this is not longer true for systems with infinite number of variables. For example, for quantum field theory or for string theory, it's no longer true. We know that these theories we cannot consider as a rigorous mathematical theorems. What is the reason for that? Why we still cannot construct them as a rigorous mathematical theories? I think the reason is that we have not yet formulated the adequate mathematical language on which we should formulate quantum postulates of quantum field theory. What kind of language it should be? I think the language should be the language of infinite dimensional differential geometry. What is the problem? Why we still have no such theory? The problem is the following, that the objects of classical differential geometry, they cannot be translated to infinite dimensions. For example, connection. We know that for connection, at least 5 different definitions, all of them are different in infinite dimensions, and some of them lose their sense. Not speaking of curvature, we know that Riemann curvature in infinite dimensions, this is absolute nonsense. Nobody knows what is this. So what should be the language of this infinite dimensional differential geometry? To my opinion, we should use the most robust language when we go to infinite dimensions. What is the most robust language? The most robust language is algebra. So we have hope that if we formulate everything in algebraic language, then we can push it to the, pull it to the infinite dimensions, and then probably this language will survive. To do that, we first should formulate everything in terms of algebra, and then try to go to infinite dimensions. So that was my motivation, at least, for learning this. Thank you very much.
Thank you, Professor Sergeev, for very philosophical remarks also. Please, if you have questions, somebody wants to ask? Yes.
The Knox-Sullivan theorem is for the real Sobolev spaces or for complex one?
It's for real.
It's for real.
But it's also extended, of course, to complex. But as I formulated, it was for real, because I was considering the symplectic form, the reaction of symplectic form.
And,
so,
yes.
Yeah.
And why 1/2? Why Sobolev space 1/2?
This is very good question. This is very good question. This is the point which I have forgotten to tell about. If I give the definition of this symplectic form omega,
Yes.
you know that for physics, what is most important? This is phase space. Phase space, we know what is this. But symplectic form is also given by God. We cannot change it. It was given by God. But this symplectic form, as I give you the formula, the biggest space on which it is